In the first two lectures of Chapter 2, we introduced the concept of entropy using the macroscopic concepts of temperature and heat transferred between the system and the surroundings. We also indicated that entropy was a measure of disorder when considering the dispersal of energy and/or matter. In the first part of today's lecture, we show, using the work of Boltzmann, that entropy can also be defined at the macroscopic level when one focuses on the statistical properties of a system. In the second part of this lecture, we discuss the spontaneity of chemical reactions under standard conditions, and through the introduction of a new state property, the Gibbs energy, we extend the formulation of the second law of thermodynamics to conditions of constant pressure and constant temperature. We start today's lecture with the discussion of the Boltzmann formula, which makes the connection between the entropy and the statistical properties of a system. To do so will require us to define the microstates and the configurations of a system. For illustration purpose, we apply the Boltzmann formula to describe the conformational properties of polypeptides and the residual entropy of solids at 0 Kelvin. We then change topic somewhat and describe calculations of standard reaction entropy changes in terms of the standard molar entropies of substance involved in the reaction, and discuss the spontaneity of chemical reactions under standard conditions. We conclude this lecture with the introduction of a new state property of the system, the Gibbs energy G, to enable us to characterize the spontaneity and the reversibility of processes under conditions of constant pressure and constant temperature. We will discover that the second law of thermodynamics is more easily applied using the change in the Gibbs energy than through calculations of change in entropy of the universe.